Okay, hello everyone. So this is the finishing of Chapter 5, and we're going to be looking at how to apply Newton's laws in a variety of circumstances here. So just to cap off what we're doing today, we're looking at interacting objects. So for example, if I had a block pushing into another block, or a car crash or something like that, that would be two objects interacting with each other. And then finally we'll close with ropes and pulleys. This upcoming Monday, October 7th, we'll be doing uniform circular motion and looking at the dynamics of circular motion. For the upcoming exam on next week, which will be Wednesday, October 9th, we'll do everything that up through Chapter 5, emphasizing topics that were not covered on the first exam up through the end of Chapter 5. There may be a couple of bonus questions related to Chapter 6. And just as a reminder, we have our homework for Chapter 5, which is due tomorrow evening. So we're trying to use Newton's laws, and we're trying to solve equilibrium but also dynamical problems. And so today we'll be looking at interacting objects. And we'll also recap Newton's laws. So the first law of Newton, what does that say? That says that if an object's in rest, it'll stay in rest unless there's an object that unless there's a force that acts upon it. And Newton's second law says something about that acceleration, which is that if you took the force and divided by the mass, then that would tell you the magnitude of the acceleration that the object would have. And Newton's third law is talking about action-reaction pairs of forces. So in other words, you can think of it as if A pushes B, then B pushes A, right? So there's two members of this action-reaction pair, and they point in opposite directions, and they're equal in magnitude. And we'll find that just being opposite in direction and equal in magnitude doesn't necessarily mean that they're an action-reaction pair, and we'll get to this in just a second. So if objects are in contact, one of the things that we need to do is draw a free body diagram to solve these kinds of problems. If they're in contact, you also know that the accelerations of both the blocks, in this case block A and B, are the same. So we have to consider the motion together. So take a look at this, and I'm not going to pause for irregularly long time. I'll just let you push pause on your video to figure these out. Which of these forces do you think is an action-reaction pair? Go ahead and pause for a second. Okay, so you've paused, now you're back, and hopefully you saw that even though the weight of A onto B and the normal force pointing up are equal and opposite, that's not necessarily an action-reaction pair. The one that is an action-reaction pair is the frictional force. So in other words, A has a frictional force on B, B has a frictional force on A. So that's an important point moving forward in understanding how to apply Newton's third law. So let's take a look at how to apply, let's not solve this crazy one just yet. Let's solve one where we're pushing a block, but it's pushing into another block. So I'm going to move back and forth between video mode and the slides. So I'm going to just draw myself a picture here. Oops, my pen seems to have gone out. Let's see if I can get a different pen. So it shows two blocks. Block A is 5 kilograms, and block B is 10 kilograms, or the masses. And I'm pushing block A with a 3 Newton force. So this is the force of pushing is equal to 3 newtons, 3.0 newtons. And so we're basically asking the question, what force does block A exert on block B? Well, in order to do this, we might separate the forces and think about a free body diagram for each of the forces. So I'm going to go ahead and draw that right now. So here's kind of my sketch, and I'd like to draw a free body diagram that sort of captures the motion for each of these, captures the balance of forces for each of these blocks. So maybe you can try that with me. If we have this scenario here, if this is my block A, then what are the forces on it? Well, the easy ones are the weight of block A and the normal force that goes back, points up in the opposite direction. And then we have the force of the push, or the force of the hand, right? But then block B must also be pushing up against block A. So there's going to say the force of block B on A. Okay, so those are all of our vector forces here. I'll put little vectors above them. Let's take a look at block B. Block B, well, we know because of Newton's third law, this action-reaction pair, that if block A is pushed upon by block B, then block B must be pushed upon by block A. So therefore, we must have equal and opposite forces for the force that block A has on block B. We also know that block B has a weight of its own. That's equal to the mass of B times G. We can also put this here, mass of A times G. And we also know that there must be a normal force of B that balances it. So that's our sketch for our free body diagrams for A and B. So just going back to the slides here, you can see that this is our picture, very similar how we drew it in this diagram. And now we get to solve the motion. Well, one thing that we can notice here is that we only need to worry about the x direction of motion for right now. We can see that there's nothing really happening in the y direction for this problem. So we can say that for block A, the force of the hand minus the force of B on A, that's equal to the mass times the acceleration of x for block A. Also, you know that this acceleration of block A is the same as the acceleration of block B. So that's another sort of hint that we have here. So I'll go ahead and just write that down here, just as we have been doing all along, is that we've been writing a sum of forces. So for block A, the sum of forces in the x direction is equal to force of the hand minus the force of B on A. And that's equal to mass of block A times the acceleration. And I'm just going to leave that as the acceleration because, you know what? We don't care that it's the acceleration of A or it's the acceleration of B. It is just simply the acceleration, and we know it's the acceleration of both. Now let's do the same thing for block B. For block B, the sum of the forces in the x direction is equal to, well, it looks like there's only one. It's the force of A on B. But that's also the same thing as the force of B on A. They are the same as each other. Right? And that's going to be the mass of B times the acceleration. And notice that I said it was the same acceleration here. So I'm just going to highlight that point here, is that this and this, that A of block A and A of block B are the same. So we're just going to call them as A. Okay, so that's why I called these A's as the same. So now we're going to crank through a little bit of math here. So if this is true, the thing that I'm really wanting to get is, well, what did the question ask? It actually asked, what is the force of going back, what is the force that A exerts on B? So in order to do this here, we're seeing that, well, it's this thing. Sorry, let me move to the video screen. It's this thing right here, right? The force of A on B, right? But the problem is that we don't know what the acceleration is yet. So one thing that we can do is we could solve for the acceleration here for this one, and then plug it into the equation above. And so let's do exactly that. So so moving forward, if these are my starting equations here, I can solve this equation here. Acceleration is equal to FAB divided by MB. And then I'm going to plug this in for the acceleration here. So I'll have F hand minus FAB. Keep in mind that FAB and FBA are the same magnitude. And I've taken care to include the signs by either writing a plus or minus in the equation, is equal to MA times A, which is now this one here, which is going to be FAB divided by MB. So cool, we have now an equation that has all the things that we know, like the force of the hand, the masses of the two blocks, but what we don't know is the force of AB. So here's how I can solve an equation like this. FH minus FAB minus MA over MB times FAB is equal to 0. So I just brought the this term over here. I brought this term over here to the left-hand side. Now I can group, since I see that I can use the distributive property and group these two terms here. I can say FH minus FAB times 1 minus MA over MB, that's equal to 0. So we're getting close now to being able to solve the problem. And now I can bring this whole term over to the right and say FH is equal to FAB times 1 minus MA over MB. And finally I can divide this parentheses thing and say FH divided by 1 minus, oops, let me move this up a little bit, FH divided by MA over MB is equal to FAB. Good. So that's our solution here, and if we plug in the numbers, for example 3 newtons, and then 1 minus mass of A, which was 5 kilograms, divided by mass of B, which was 10 kilograms, we're going to get 1 minus a half, and so that equals to, and I'll just write FAB, equals to 3 divided by 1 half, so 1 minus a half is 1 half, which is going to be equal to 6 newtons. So let's see if we're right. So, oh, I maybe made a mistake here. Let's see, what did I do wrong? Oh, I did make a mistake. Why did I make a mistake? I made a mistake because FH minus FAB is to MA. And then oh, I see it now. Okay, so I made an arithmetic error here. Can you see where I made the mistake? So where I made the mistake here is that I have this minus, and so this is a minus and a minus, so this should actually be plus, 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 plus. So then this is now 1 plus a half down here, so we have 3 divided by 1.5, or 3 halves, and so when I divide 3 divided by 3 halves, then it's equal to 3 divided by 3 times 2, or in other words, I have 6 divided by 3, which is 2.0 newtons. So my arithmetic error came in, everything up to this step was correct, and I just had to be careful about when I did the distributive property to make sure that I also distribute the minus sign. So, well, you saw me make a mistake. I hope that you can follow along with what I did here. And we ended up with 2 newtons. If you still need some help, then also there's a good explanation in the slides. So that is our force that would be from A to B, and also consequently would be the force from B onto A. And those are our action and reaction pairs. Now we're going to take a look at ropes and pulleys here. So I find this slide to be a little bit too technical, honestly. We're basically just trying to say, you know, yes, it's true that there should be an acceleration of the rope, but what it's saying is that we're assuming from all these problems that the mass of the rope is 0. So in other words, you don't need to draw a free body diagram for the rope because the mass is 0. I think that's pretty much what's being said here in this slide, and they just went into technical detail to hope convince you. But massless ropes, okay? Never thought it was a thing? Well, now it's a thing. So the tension is usually the magnitude of the force pulling on an end of the string or rope. So in this week's lab, you actually had the experience of using a string to pull a low friction cart, and then you draped the string over a pulley, and you let this weight on the other side go down, and then that pulled the cart across. So that was what was transmitting the force. So let's just try an example here. I think the examples are the best ways to learn, in my opinion. If you have a box and it's pulled at a constant speed with a rope, and it makes an angle of 25 degrees with respect to a wooden floor, what's the tension in the rope? So it's pulled at a constant speed. That tells us that the acceleration is 0. So let's start fresh with a new piece of paper, some new ideas. So we have, I'm going to bring this slide over here just so I can see it. So a wooden box, and we have the wooden box, and it has a mass of 22 kilograms. So I'll just write 22 kigs in here. And it's being pulled at a constant speed with a rope that makes 25 an angle of, and I could draw it as something like this, and it's being pulled up, and it's at a 25 degrees angle up with respect to the wooden floor. What's the tension in the rope? So we know that the acceleration is equal to 0. That's sort of some kind of secret information that was given by the fact that that it's moving at a constant speed. I'll say because v equals to a constant. The other thing is that we should draw a free body diagram. So the things that I can think of that are going on here are the weight of the box, right? So here's the weight, here's the normal force. Notice I didn't have to do A or B this time because, well, there's just the one box, right? And then we have this weird tension thing that's pulling off into this direction. So why don't I break it up into, if this is the tension pulling up into to the right, we can start getting used to just thinking about it as a part that's pulling to the right and a part that's pulling up. Almost as if, like, imagine there were some sort of, I don't know, some magical creatures that could see what was happening, and then they would divide up so that there would be only the guys who push up and the guys who push to the side, right? They just like kind of break it up, right? So we can see from this, if this is our angle of 25 degrees here, that this must be t times the sine of theta, right? That's the opposite. This must be t times the cosine of theta. This is a skill that I want you to get really familiar with, is in terms of breaking up into the components. So if it's not quite familiar to you, I encourage you to practice and make it more fluid for you. This is using the definitions of this so-called SOHCAHTOA. So here, then I have a tension, the part that goes up, which is t sine of theta. And then I also have a part that pulls to the right, which is going to be t times the cosine of theta. So that's everything. Those are all the forces that we care about that's pulling on this thing. So basically, we need to figure out what the tension in the rope is. So here's the thing, is that this problem is basically imagining that there must be also, because I guess what I'm thinking here is that if this was the only force involved, then there'd be some kind of problem, right? There wouldn't be, there would not be it would be accelerating, right? So we know that there's got to be some kind of frictional force here going in the opposite direction. So we know that the sum of the forces in the x direction is going to be t cosine theta minus the force of friction, and that's going to be equal to mass times acceleration, but acceleration is 0. The other thing that we know is that the sum of forces in the y direction is equal to the normal force plus t times the sine of theta minus the weight, which is, I'm going to just start now writing as mg. We also know that that's equal to 0 because it's not accelerating up or down, it's staying on the floor. So we're trying to figure out what the tension in the rope is here. So it looks like we kind of have two unknowns and we have two equations, and so we should be able to solve that. One of the things that I might do is, for example, I could say, oh, we also have the normal force, which is unknown. So let's see here. So we have the frictional force is unknown. And the normal force is unknown. Oh, I think I understand what's going on here. The catch with this problem is that we know that the frictional force is going to be equal to mu kinetic times the normal force. So what we can do then is that if I take this equation over here to the side, is I can say that t cosine of theta is equal to mu k times the normal force. Or in other words, the normal force is equal to t cosine of theta divided by mu k. So that means that I can actually now plug in the oh, you know what else I can do is also from our slides last time, we know what the coefficient of friction is. Oops. Let me just bring up the last time slides. And if you remember, the coefficient of friction of, oops, where is it? I think it was somewhere right around here. Wood on wood. There it is. Okay. So wood on wood, the kinetic friction is 0.2. Okay, good. So that was the other secret missing information. That was a little bit of a trickster problem for sure. So we're going to say that this is, we're going to say that mu k is equal to 0.2. And that was something that we looked it up. Okay. So then this is going to be, well, t cosine theta divided by 0.2, so divided by 1/5. So it'll be 5t times the cosine of theta. So I'm dividing this is equal to 1/5, basically. So we can plug in this n into here, and then I hope that we can then solve for t, the tension in the rope. So let's try it. So we have 5t cosine theta plus t times the sine of theta is equal to mg. Okay? So in other words, we have t times 5 cosine theta plus the sine of theta is equal to mg. Let's see, are all those things that we can figure out? We know that theta is 25 degrees. We know that sine, right? We can figure those out. And then mg. So t has got to be equal to mg divided by 5 cosine of 25 degrees plus sine of 25 degrees. So that is our challenge here. Mg, of course, is going to be equal to 22 times, we can just use 9.8 or we can even use 10 just to be kind of a little bit, you know, how do you say, going off the cuff here. So let's do a calculation. I'll just bring out my favorite easy calculator, which is just how to use Google, oops, and we can just try doing mg, which is 22 times 10, divided by 5 times the cosine of 25 degrees plus the sine of 25 degrees. And notice my use of parentheses to make sure it all works out. And then finally we can see that our unit here is 45.6, that's 45.6, and the answer should be in newtons. That is our unit of force. So the tension in the rope would be 45.6 newtons. That was a rather complex problem, and there was some secret tricks in there. One of them being that we had to have figured out what mu k was. It wasn't something that we knew that we were given. Now, in an exam problem, I would give you what the coefficient of friction is if it's needed. I won't ask you to memorize or to copy down the table for what's the coefficient of friction between two surfaces. But I might give you a table, and then based on that, you can look it up. So anyway, so that's our solution. You notice that the problem-solving strategy is the same in every case. I draw a picture. I write down the things that maybe I didn't know were kind of assumed in there, and then I draw a free body diagram. Based on that, I sum up the forces in the x direction and set them equal to mass times acceleration, which in this case was 0. And so sum up the forces in the y direction and set them equal to mass times acceleration in the y direction, which was also in this case equal to 0. Let's take a look at a situation now where the sum of the forces is not equals to 0. So such a situation might be where this case where you saw in the lab, or if you haven't taken the lab yet, that you're going to see very shortly, which is that the tension in the string, if this pulley is not you know, some massive pulley, if it's an ideal pulley, so to say, a massless frictionless pulley, right? So we're trying to make idealizations. Then the tension in the string is the same both on the downside and the upside. So let's take a look at an example that uses this kind of thing here. So we have a 200 kilograms set used in a play, and it's used in the loft above a stage. The rope holding the set passes up and over a pulley and then is tied backstage. The director tells a 100 kilogram stagehand to lower the set. When he unties the rope, the set falls and the unfortunate man is hoisted into the loft. What is the stagehand's acceleration? So, hopefully that picture makes sense to you. Maybe take a moment to see if you can draw yourself a picture of what you think this motion looks like. So, I have sort of a simple picture of like this. Here's the ground, here's the person. Somehow they must be tied to the ropes. Maybe they're wearing a harness or something, hopefully. And it goes up to this pulley, up and over, and then there's this big case of stuff. That's kind of the basic picture I have. So for the person, this is my person here, it looks like that they have a weight, so the weight of the person, and that there's a tension in the rope. For the big package here, well, I won't call it P for package, but we'll call it the box, right? So the box B has a tension that's pointed up, and if pulleys really just redirect the tension, then it's the same tension. So in other words, this is a Newton's third law pair just in disguise, that the tension that's being pulled through the rope from the box to the person is the same that the person has on the box. There's also the weight of the box. So we're going to have to be a little clever here with the way that we designate the acceleration, but we can draw our free body diagram to look something like this. We'll say that the acceleration for the person is going up, so the acceleration going up. But notice that if the person goes up, we're going to also call that same acceleration going down for the set. Okay, so they used S for set and M for man. So basically, we can see that our free body diagram for the person, right, they should be imbalanced, right? There should be the tension here and the weight of the man, and then there should be the weight of the box, or the weight of the set, and there should be the tension that pulls up. And that tension should be the same for both cases there. But notice how that the net acceleration is this way, the net acceleration is this way. So if we write the sum, oh, I'm so sorry, I didn't switch back to the picture here. So here's our free body diagram for each of the. This is for the man, this is for the set, and so if we took the man situation here, the sum of forces in the y direction are equal to, well, we have tension in the positive direction minus the weight of the man is equal to the mass of the man times its acceleration. If we look at the set here, I'll just write that as S, then the sum of the forces in the y direction are equal to, now keep in mind this time down is positive, right? So we'll say WS is positive minus the tension is equal to the mass of the set times A. So those are our two equations that we have working with here. And so that's what they've shown here. And they reduce it down to two different equations, which, let's see, what we're trying to figure out here is we want to know the acceleration of either the set or of the person. It doesn't actually matter. And your book gives you a strategy for being able to solve this set of two equations because, well, we want to know A, right? And that A is the same, right? It's either the person or they say man in the y direction, but that's the same as the acceleration of the set in the y direction as well. So using that, I'd like you to try and see if you can solve those two equations. For example, what they do is they solve one of them for t, and then they plug it in, and they find that they get the acceleration as the difference of the masses divided by the sum of the masses times the acceleration due to gravity. So just reiterating here, I won't exactly retrace all their steps here, but I just say that these two equations here, you can solve for tension and then plug that into the second equation, and that will help you to solve the problem. So finally, the solution then is that the acceleration is equal to the mass of the set minus the mass of the man divided by the mass of the set plus the mass of the man, and then times the acceleration due to gravity. So in other words, you can actually check things like, well, what if the mass of the set was equal to the mass of the man? Well, in that case, that would be 0 and there would be no acceleration. Or you could say, well, what if the mass of the set was super, super huge compared with the mass of the man? You could say, what if this is 100 and this is just 1? Well, that'd be 100 minus 1, which would just be 99, right? divided by basically 101. So you get almost the acceleration of gravity, right? So those are some kind of example cases for how you can make sense of your solution. So just to summarize, the way that we solve our problems is we draw a picture, we try to see what the accelerations might be, and then we use Newton's second law in component form to solve for our answer. The important part is to make sure that you separate the x and the y components. If they're in equilibrium, then the acceleration in the x direction is 0 and the acceleration in the y direction is 0. But we found that we also saw some situations where the acceleration is not necessarily 0. Okay, so moving on, we'll also just briefly discuss some of the Mastering Physics questions. I need to take a break for just a moment, and then I will start back up the recording and answer a couple of the Mastering Physics. Okay, so just taking a look now at some Mastering Physics problems. I'll just go over a couple of the high points here. Maybe we can take a look at problem 5.2. This is the one with the parasailing. And hopefully it'll load here. Okay, very good. Oops. Oh no, I just showed the answer. Oh my gosh, how to not show the answer. Oh boy. Okay, there we go. So, in the sport of parasailing, a person is attached to a rope and being pulled by a boat. So, when a rider is towed at a constant speed by the rope, it is an angle of 15 degrees, and the tension in the rope is this, 2,300 newtons, and the force of the sail on the rider is 30 degrees from the horizontal. So, there's a few things going on here. Let me go ahead and I'll put this over and so we can look at the screen, and we can take a look at, well, what does your picture look like for this situation? So a person, so I mean, I can think about, here's the water, there's some kind of motorboat here, and then there's a line that goes up to the person, and just draw them as a box, and that they have the sail is pointed up at a 30-degree angle with respect to the horizontal, and that this angle here is at 15 degrees with respect to the horizontal. And so we're supposed to figure out what the weight of the rider is. Well, the constant speed is the important point, and we could try drawing a free body diagram, which basically we can say that there's a force of the sail that points up, and there's a force of the tension that points down and to the left, and then there's the person's weight. Now there's no normal force in this case, right? The person is not on a surface, right? So those are the forces at play, and we know that this angle is 30 degrees, and this angle here is 15 degrees. So again, if I were to break this problem up into sort of just things that are in the vertical direction and just things that are in the horizontal direction, my diagram might look something like this. My force of the sail, so we can say force of the sail, and we could say times the cosine of 30 degrees, and this here is the force of the sail times the sine of 30 degrees. Similarly, the tension here can be broken up into tension times the cosine of 15 degrees, and then the down part is going to be the tension times the sine of 30 degrees. So just drawing that all out more clearly, we have the weight, which is mg, is equal to the weight. We have also t times the sine of 30 degrees, and we have the force of the sail times the sine. Oh, I'm sorry, I said 30 degrees. This is wrong. This is 15 degrees here. This is 15, and this is the sine of 30 degrees. So that's our vertical parts, and our horizontal parts are that the force of the sail times the cosine of 30 degrees, and the tension times the cosine of now 15 degrees. So in other words, this is a kind of problem where we can sum up the forces in the x and in the y direction. So when you do that, let's sum up the forces in the x direction. We have the force of the sail times the sine of 30 degrees minus the tension times the sine of 15 degrees minus the weight is equal to 0. So gosh, if we could only just get something that's just in terms of the tension in the rope. Well, fortunately we can do that because we have the x equation to deal with. So this is the y equation, but from the x equation, let's sum up the forces in the x direction. And when we do that, we'll see that the force of the sail times the cosine of 30 degrees minus the tension times the cosine of 15 degrees is equal to the mass times acceleration in the x direction, which is also equal to 0. Remember that this is a constant speed problem. So the hint that I'll give you now, I guess I've kind of helped you to work through this problem, but the hint now is to say, well, let's solve this second equation here, the x equation, for the force of the sail, and then plug that value in up here. Then we'll have an equation that just involves the tension and the angles, and then from there we'll be able to solve for the weight in this problem. Okay. Good. I'm going to also go over one more, which is going to be problem 5.24. So this is talking about a mountain goat, and the mountain goat is standing on the mountain, but it's at an angle of 60 degrees from the horizontal. So here, I'll draw a picture here of my mountain goat. We have a very, very steep mountain that's 60 degrees. And here's our mountain goat right there. And we're being asked, well, what is the normal force of a mountain goat that weighs 700 newtons? That's a force that's going straight down. It has a normal force this way. And there must be also some friction that's going this way. So keep in mind, remember this issue here is that this angle is the same as this angle. That's the important point. So in other words, if I were to just draw a free body diagram like this, right? So I'm almost like I'm kind of rotating this thing around. This is actually a nice chance where I can use the camera to do this kind of thing here. This is our normal force. This here is, remember that there's a weight that's like cosine, right? So weight times the cosine of the angle, and then a weight times the sine of the angle, right, is pointed in this direction here. So weight times the sine of the angle is pointed here, weight times the cosine of the angle is down, or not down, but down in my new coordinate system here, and then the force of static friction is pointed this way. So the cool thing that we can do now, so that's my picture, and this is my sort of my new axis here, my x and my y axis, right? Looking in this way here, I can sum up the forces in the y direction and say that this is the normal force minus w times the cosine of theta. And that is equal here to 0 because this is an equilibrium situation. The goat is not moving. And so if I solve this, I can figure out then what the normal force is. Similarly, you can sum up the forces in the x direction, or the sort of our modified x direction here, and find out what the force of static friction is. So hopefully that gives you enough hint for that one. Thank you very much for watching. I hope this was useful for you. I encourage your feedback, and I wish you the very best as you work through the homework.